In the silence of space, our blue planet hides vast water underground. Welcome to Groundwater Recharge. Groundwater is the water that is found beneath the Earth's surface. It does not exist in underground rivers or lakes as many people might imagine. Instead, it fills small empty spaces known as pores within soil, sand, and rock formations. A large underground body of water-bearing rock or sediment is called an aquifer. Aquifers act like vast natural sponges, holding immense quantities of fresh water, which people around the world depend on every day. The long-term health of this resource depends on groundwater recharge, the essential counterbalance to groundwater use. The journey of water from the surface to an aquifer is governed by gravity and geology. It begins with rainfall and melting snow. The first step, infiltration, is when water soaks into the topsoil, moving past grass, roots, and small pebbles. It continues downward through the unsaturated zone, where pores contain both air and water, a deeper movement known as percolation. Percolating water descends until it reaches the water table, the boundary above the saturated zone, where pores and fractures are completely filled with water. At this point, water joins the groundwater system, completing recharge and nudging the water table upward. Natural recharge is gradual, varying with land characteristics and climate. Rainfall and snowmelt are primary sources. Rivers, streams, and lakes can seep through beds and banks to adjacent aquifers during high flows. Wetlands, marshlands, and swamps hold water and release it slowly, providing steadier recharge than brief storms. Gentle, prolonged rain on flat, vegetated land favors infiltration. Intense downpours on steep rocky slopes drive runoff. Soil, vegetation, slope, and rainfall intensity together control how much water soaks in. Recharge comes from rainfall, snowmelt, natural and seepage from rivers, streams, lakes, and wetlands. During high flows, water can percolate through beds and banks, replenishing nearby alluvial aquifers. Wetlands act as landscape sponges, slowly seeping water to the subsurface. Artificial recharge supplements nature through two approaches: direct surface and direct subsurface methods. Surface methods spread water over permeable land so it percolates down. Infiltration basins and percolation tanks. Subsurface methods use recharge wells to deliver water directly into specific aquifer layers. Common engineered tools include recharge wells, percolation tanks, check dams, and infiltration basins. Effectiveness depends on soils. Permeable sands and gravels favor infiltration. Clays impede it. These methods capture stormwater that would otherwise rush into drains. Recharge balances withdrawals, stabilizing groundwater over time. Managed properly, recharge supports water security for people and nature. A recharge well is a deep structure that injects water directly into a target aquifer. First, source water is treated to remove sediments and contaminants that could clog the well or pollute the aquifer. The treated water is piped to the wellhead and directed down a central pipe called a casing. The casing extends through impermeable layers until it reaches the target aquifer. A perforated screen allows water to flow out into the formation, replenishing it from within. Percolation tanks use surface infiltration and are simpler to build. They require permeable soils and a relatively shallow water table. Sandy soils promote deep infiltration. Clays cause surface pooling. An earthen embankment forms a wide, shallow basin. During rains or canal surplus, the basin is filled. Over days to weeks, water percolates through the bottom and filters through soil and gravel layers, eventually joining groundwater and raising nearby water levels. Check dams are small barriers built across seasonal streams or gullies. They may be made of stone, concrete, or earth. When runoff arrives, the dam slows the flow and forms a temporary pond. Longer contact with the bed and banks allows more infiltration, recharging the shallow alluvial aquifer. Recharge success depends on soil type, land use, vegetation, slope, and rainfall patterns. Sands and gravels have large connected pores that transmit water quickly. Clays and silts have tiny, poorly connected pores, causing slow infiltration and more runoff. Impermeable urban surfaces funnel rain to drains, drastically reducing natural recharge. Vegetation creates soil channels and organic sponges that enhance infiltration. Multiple gentle, prolonged events recharge more than one intense storm, delivering the same volume. After drought, baked topsoil can resist infiltration, increasing initial runoff. Recharge prevents aquifer depletion, halting or reversing falling water levels. It supports agriculture by providing more reliable supplies and resilience to drought. Healthy groundwater sustains river base flow and ecosystems during dry periods. Capture and soak structures reduce peak runoff and lower downstream flood risk. Percolation through soils filters sediments and helps break down pollutants, improving water quality. Some projects use treated wastewater, adding a low-cost polishing step in the subsurface. The benefits span water supply, farming, flood mitigation, and water quality. Groundwater recharge is a cornerstone of sustainable water management. It keeps hidden reservoirs full, builds drought resilience, supports farms, reduces floods, and cleans water. Today, the need for proactive, science-based management is clearer than ever. We must manage recharge with care and long-term vision to safeguard water for generations. By understanding the process and applying proven methods, we can protect and replenish our hidden water supply. From space to soil, safeguarding groundwater secures our future.